position in an uh, sorry we are talking about a change in an object's position over a period of time relative to a reference point. And when we say reference, we can give an example. Say we have a car, and there is a driver and a passenger, and there is one person standing outside the road. And if you see this car is moving, and from the perspective of the driver and the passenger, both the and passenger will see each other as at rest, meaning the driver uh, is not at rest, sorry, not changing position with respect to the passenger. And the passenger position is also not changing with respect to driver positions. However, if you see from the perspective of this person, he is standing up far away from the car, both the driver, passenger, as well as the whole car is moving away from this position in direction. So whenever we are defining the motion, we need to have a point of reference. With that, let's recall the different terminologies we have defined so far. We defined motion as the change in position in a time interval with respect to some reference, and then we have time. We represent t1 t2 as an initial time and final time of the observation, and we use this Greek symbol delta to show the change, and we say delta t is equals to change in time, or we can say delta t is the time interval, and it's given by final time minus initial time, and basically this is the elapsed time of observation. And then we also talked about the position, and we represented position with this variable x, and we used x1 as the initial position at the starting time, x2 as the final position at the ending time, and again we used sorry and then and again we used this delta x to show the change in position, and we define the change in position as final position minus initial position. And we also said sometimes instead of x we'll use d to represent a change in distance. And then we talked about the velocity, and we defined velocity as the ratio of change in position over time interval. And we also showed that we will represent v1 as the initial velocity at the starting time, v2 as the final velocity of the object at the end time, and uh, b average, and we defined average velocity as the ratio of change in position over a time interval. And we also defined the average velocity in terms of instantaneous velocities, which we defined as the average velocity we defined as sorry average is equals to average of all instantaneous velocity. So if we have two instantaneous velocity v1 and v2 at initial position and final position, then the average is given by v1 plus v2 over 2. With that, we will define a new term known as acceleration, and we will use the symbol A to represent the acceleration. Uh, Acceleration is a fundamental concept in motion. It is defined as the ratio of it is defined as the ratio of change in object's velocity over a period of time. So, in other words, we can say acceleration is the rate of change of velocity. Rate of change of velocity. So previously we defined velocity as the rate of change of position, and now we can define acceleration as the rate of change of velocity. Here we can say, if you look at this, sorry, if you look at this animation, we should be moving for here. You can see the velocity is changing as the time is passing. Initially the velocity started at a lower value, and now at the final positions you can see at time 0.47 the velocity is increasing from 2.8 to 3.6 and so on. Basically, as the time passes, the velocity changes from one value to other value. And let's say the velocity of a car relative to some coordinate system is v1 at initial position at time t1. Later at time t2, after the car has sped up, its new velocity is v2. So the final velocity is v2, initial velocity is v1. The change in velocity experienced by the car is like we did for the position, the change in velocity is final velocity minus initial velocity. Now if we want to define the acceleration in terms of mathematics, we can say acceleration is equals to change in velocity over a time period, and change in velocity is basically final velocity minus initial velocity, and change in time is final time over minus initial time. And like we represented the velocity as the slope of displacement versus time graph, we can also represent the acceleration as the slope of velocity versus time graph. And again, we have to mention that the slope of the velocity versus time graph represents acceleration. That means if the slope increases, that means the acceleration also increases. The steeper the curve is, the higher the acceleration will be. Let's say example again. We have three cars moving, and we can see in this animation the green car is at a constant velocity. We can see here green car, all the car starts at the same position at the same velocity, and we can see the blue car is accelerating fast, meaning it's speeding up quickly, and then red car is following it. Red car is also speeding up, but in a lower rate compared to the blue car, and the green car is not speeding up and it's moving at a constant speed. So if we were to plot here velocity versus time graph, we can see for green car, the velocity is not changing. It started at some velocity and then it remained at the same velocity. So this is constant velocity. And then for red car, it started at some point and then with some value it's changing the velocity, change in velocity. And then we have the blue car, and we can see the slope of the blue car is the highest, meaning at the same time it will cover the highest distance, and at the end of the time the velocity will be highest velocity for blue car at the end of the time interval. Now this is velocity versus time graph. What will happen if we were to plot position versus time graph? Now for constant velocity, we know the velocity is not changing. It is started at time 0 and position 0. So we can see, sorry, let's use the proper color. So green car, all three cars started at position 0 and time 0 as well, and the green car is at a constant velocity. That means at every time interval it is covering the exact same displacement. For example, for 1 second it will cover this distance, for the second this distance, third second, fourth second, fifth second, sixth second, and so on. The distance will be same for each time interval. So the distance in each case is equal. So we have a straight line, meaning the slope is constant throughout the line. And if we look at the red one, it started at the same point, and for the first time interval it covered the same distance, but as the time passes, for the second it accelerated a little, and instead of being in this position, now our red car it adds this position because it's speeding up, it's covering more distance compared to the green car, and as time passes it's accelerating even more, and it's accelerating even more. We can see as time interval changes, first interval, second interval, third interval, fourth interval, we can see for the same time period in each scenario the distance covered is increasing comparatively. So we can say our graph would look something like this. Let's not do this because we said all the cars were starting at the same point. We can say this because the slope here is the same as the green car, and as the time passes the slope of the red curve increases. And let's make it proper. So this is green and this is red. Instead of a straight line we have a curve, and for the blue car, for the same period of time it increases rapidly. So here, so these two lines will be non-linear line because the car is accelerating, and every second the position it covers is different than the previous second. And for green card the line is straight, meaning every second the car will cover the same distance regardless of which time period you are looking at. Now let's see an example uh, mathematically. Suppose a car is traveling at an initial velocity of v1. So initial velocity is given at the initial time period. So initial time is given, t1 is 2 seconds. Then the car accelerates to final velocity 10 meter per second, and the time at the final time is at 5 seconds. And the question is asking what is the car's acceleration. And by definition of acceleration, we know the acceleration is the ratio of change in velocity to change in time. And we can write this at final velocity minus initial velocity over time period is final time minus initial time, and which is time interval. So this is 10 meter per second minus 4 meter per second, and time is 5 second minus 2 second is equals to this is 6 meter per second over 3 seconds. And if you look at here, the unit, this is second, this is also second, so we have 2 meter per second, and this is the unit for acceleration. And we can see as 1 second, sorry, so this is the acceleration. What this means, the unit 1 meter per second square means every second the velocity increases by 2 meter per second. So every second, if the acceleration of the car is 2 meter per second square, what we can say is that every second the velocity of the car will increase by 2 meter per second. So for the we are looking at 3 seconds here, and we said the initial velocity is 4, final velocity is 10. If we want to look at the time, the velocity at say the uh, first second of the acceleration, then we can say it started from 4, and every second it will increase by 2. So at the end of the first second, the velocity will be 4 plus 2 is equals to 6 meter per second. And the second question is asking what was the average velocity of the car. And we know average velocity is the average of all the given velocities here, final velocity plus initial velocity over 2, and final velocity is 10 meter per second, initial velocity is 4 meter per second, and divided by 2, 14 meter per second over 2, this is 7 meter per second. And now how next question is how far did the car travel. And from the previous section we know that velocity is equals to change in position over time interval, or in other words, displacement over time. And since we are not talking about the path, like which way the car is moving, we are considering a straight line. We can also say this is distance over time, and if we don't represent the velocity, direction, we can say is the magnitude is the same as the speed. So we can use this relation to calculate the distance traveled by the car. So here V average is equals to delta x over delta t, and we just calculated from the previous section our average velocity is 7 meter per second. So 7 meter per second is equals to displacement over time, and we know 7 meter per second is equals to delta x we are looking for, and time interval was 5 second minus 3 second. Or if we want to simplify it, we can do a cross multiplication and multiply 7 times this is 2. Let's also write the unit. 7 meter per second times 2 second is equals to delta s. Now if you see here, this second is a numerator, denominator, and this is a numerator, so we can cancel the second and second symbol. So we have delta x is equals to 7 times 2 is equals to 14 meters. So the car traveled a total distance of 14 meter, and we calculated this total distance using the average velocity. And this is also simplified here. You can, solving this equation, we isolated delta x, and the final formula is delta x is equals to average velocity times time interval. I'm sorry, this time was 2 seconds, not 3 seconds. So this will be times 3, and 7 times 3 is 21 meter. And now let's look at next question. What is the acceleration of a car that is traveling at 40 meter per second and comes to a stop in 5 seconds? So here this one is an interesting question because the final velocity here is not given directly, and you have to infer from the question what is the final velocity. Let's see here, initial velocity v1 is equals to 40 meter per second, and what this question says is the car comes to rest, come to a stop in 5 seconds. That means final velocity is 0 meter per second, meaning the car is at rest. So when it says car comes to a rest, that means the car is not moving, and basically the car is not moving and the velocity is 0. And time interval delta t is 5 second. Now we have to calculate the acceleration, and we know acceleration is delta v over delta t, and change in velocity is final velocity minus initial velocity over time 5 second. And here 0 minus 40 is minus 40 meter per second, and this is 5 second. And if you simplify it, this is 8 this is minus 8 meter per second square. And now we can say the acceleration of the car is minus 8 meter per second. And sometimes on the negative acceleration, you need to be clear that this negative acceleration is sometimes representing that the car is slowing down. However, sometimes it may just represent that car is moving in a negative direction. So the negative acceleration could mean two things. It could mean it's either slowing down, or the negative acceleration could also mean accelerating in negative direction. Here we can see that the distance, the velocity is velocity is changing from 40 meter per second to a stop, meaning come to a stop, that is 0 meter per second. So we can say the car is slowing down. In other term, slowing down is also called a deceleration, and the final answer is minus 8 meter per second. And now we use this graphical method to represent velocity as the slope of a position versus time graph previously. Now we can also use the same approach, but instead of creating a position versus time graph, we can plot a velocity versus time graph. And if you see here, the equation of acceleration is change in velocity over change in time. Basically change in velocity is rise and change in time is run, and the ratio of rise over run is the slope, and slope is equals to rise over run. And here rise is delta x, delta t, so the acceleration. And basically the slope of velocity versus time graph gives us the acceleration. And again the line here is a straight line, meaning the slope of this curve is same at any time interval regardless of which point. If you take slope here, here, the slope will be the same, meaning the straight line representing a constant acceleration. The slope is constant throughout this line, so basically and this curve represents a constant acceleration. And we can also see the velocity is going from a smaller number into a larger number, so we can say the acceleration is positive, and sorry, the the slope is positive and the value is going from v1 to v2. That means uh, the velocity will increase as the time passes by. And now let's go back to the same curve like we did in position versus time graph. Now we have in our y-axis velocity, in our x-axis time, and we need to figure out which of this car are moving with the highest acceleration. And again, the steeper the slope is, the highest the acceleration is. So this is the steepest, the highest slope of the slope uh, curve. So this is highest acceleration, and then this is the smallest slope, so this is lowest acceleration, and this is in between A and C. And again, all these three curves are straight line at some inclination, so the slope is the same regardless of what point you are taking. So all of these accelerations are constant acceleration. Now let's look at one more example here. If you look at the change in velocity delta v, for example, if this is your time t1 and time t2, and you want to calculate the slope for regarding final velocity and initial velocity at time interval t2 minus t1, so the velocity v1 and v2 are the same at same point, that meaning v2 minus v1 is 0. So the slope is equals to 0, and if the slope is 0, then acceleration of this object is 0. So if the velocity versus time graph is a horizontal line, that means there is no acceleration. And we can extend this relation and find some more equations to solve a more complex problem. And let's find out how to calculate velocity at a different time, as well as how much distance will an object cover with certain acceleration and certain initial velocity. And we know the average velocity is the change in change in position over change in time. And if we rearrange it, we can write this average velocity. We can do a cross multiplication, b equals to delta x over delta t. We can assume that there is 1 here, and if we cross multiply it, b delta t is equals to delta x times 1. Therefore delta x equals to v times delta t, right? We can simplify it and solve for delta x. And we also know that acceleration is a rate of change of velocity with respect to time. So rate of change of the ratio of change in velocity over change in time, and the change in velocity is v2 minus v1 over delta t. and we can again we can do a cross multiplication here and simplify it. Say we have a 1 in the denominator, then b2 minus b1 over delta t, and if we cross multiply it we can get b2 minus b1 is equals to a times delta t, so which is written here. And now if we simplify it more and separate b2, we will get b2 is equals to we can move this b1 in the right side and this negative sign will convert into positive sign, so we will have b1 plus a delta t. So we have new relation here, b2 is equals to b1 plus a delta c, which is used for finding final velocity if initial velocity, acceleration and time interval is none. So if we know the initial velocity v1 and the acceleration of the object and the time interval is accelerating for, we can calculate the final velocity of the object. And similarly, using the same relation, we can also isolate v1 here and calculate b1 where b1 is equals to final velocity minus acceleration time delta t. So if you want to calculate the final velocity, we will use this relation. If you want to calculate the initial velocity, we will use this relation. And furthermore, we can expand this relation to calculate the distance covered by the object. So this equation we just solved in the previous slide, and we will call this equation 1, and we want to find the relationship between acceleration, velocity and position. So in the previous in the previous equation we calculated the final velocity with final velocity in relation to initial velocity, acceleration and time, and now we want to calculate the relationship between acceleration, velocity and position. And from the previous slide we know average velocity is delta x over delta t, and if we rearrange it we can write it as the average velocity times time interval, which is b1 plus b2 over 2 is the average. So this is the average velocity, and delta t is the time interval. And then here we know we can see delta x equals to b1 plus b2 over 2 times delta t, right? And then if we go back to previous slide and look at this equation, this is the value b2 is equals to b1 plus a t square. That means this is the final velocity. If we substitute this final velocity back to this equation, what we get, b1 plus what is b2? b2 is b1 from this equation, b1 plus a delta t, and everything is as it is. So that is how we get to this equation here. And if we simplify it, now let's simply simplify it. So delta x is equals to b1. Now let's open the bracket, b1 plus b1 plus a delta t over 2 times delta t. So we just open this bracket, and now we have 2 v1, so 2 v1 plus a delta t over 2 times delta t is equals to, now let's simplify it furthermore, so we can write b1 over 2 a delta t over 2 times delta t. Now this is 2, so this is cancel, this can cancel out, so we have b1 plus, and we have 2 in denominator here, and acceleration, and these two are the same term, so delta t squared. So basically what we get is change in position is equals to initial position plus half acceleration times time period squared. And in order to simplify it, we can write a change in position as d and a change in time as t. Then we will get a simplified equation represented here. So d is equals to v1t, sorry, here it should also have delta t because you need to multiply this to both of this term here and here, so you have v1t plus half at squared. So this is our second relation. So we have two relation, b2 is equals to b1 plus a t, since we are using delta x equals to d and delta t equals to t. Then another relation is d equals to b1t plus half at squared. So we will need to remember this two equation. This is to calculate the final velocity if given initial velocity, time period, and acceleration, and this is for calculating the distance covered given initial velocity, acceleration, and time period. Now let's see an example. Here suppose a car is traveling at v1 equals to 4 meter per second, and the starting time is at 2 seconds. The final velocity then accelerates to a final velocity of 10 meter per second at time 5 seconds. What is the car's acceleration? And car acceleration is change in velocity over time. Here the change in velocity is final velocity minus initial velocity over time interval. This is 10 meter per second minus 4 meter per second over 5 second minus 2 second, 6 meter per second over 3 second, and this results in 2 meter per second square. Now the second part of the question wants us to calculate the distance covered by the car in this time interval. So the formula for distance we just derived was d equals to b1 times time plus half acceleration and time squared. Here b1 is 4 meter per second and time is 5 minus 2, so t is 5 second minus 2 second equals to 3 second. So initial velocity times time 3 second plus half acceleration we just calculated here 2 meter per second square, and squared times time is 3 second squared. And now this is 4 times 3 is 12, And if you see, this is a second in denominator, second in numerator, so that cancels out. It will be in meter plus half. 2 squared is 4, and for a unit it will be square of both of these, so meter square over second 4 time 3 sorry, this will be just a not squared. This wouldn't be squared, this is acceleration, not the time, so this should be half times acceleration is 2 not squared meter per second square, and time, this is square 3 squared is 9, second squared is second. And now if you see here, say there is a second square in denominator and second square in numerator, so we can cancel this out. So our answer will be 12 meter, and this is 2, this is 2, this will cancel out, plus, and we have meter here, 9 meter, so total 21 meter. So the distance traveled by the car, if the time interval is 3 seconds, will be 21 meter.